Hello again. In this chapter, we are going to learn a new concept that is called continuous compounding. So far, we have learned that the compounding of interest may occur in different periods. In many applications, until the end of chapter 4, we have studied annual compounding, but in chapter 5, we have learned that the compounding may occur in different periods, such as months, weeks, or days. And for that, we need to calculate the effective interest rate that corresponds to every compounding month. But here, the compounding is just going to be taken to a new level where we are going to assume that compounding occurs continuously. In other words, the length of the periods, compounding period, will converge to zero, or in other words, in a year, the number of compounding periods will converge to infinity. So that is going to be called continuous compounding. As the final section of this chapter, we are going to learn about the varying interest rates, which is rather very easy compared to continuous compounding topic. So we are just going to spare a small amount of time for this last part. So the outline is as follows. We are going to learn about continuous compounding. And of course, under continuous compounding, the payments are going to be assumed discrete again. So even though the compounding will occur continuously, the payments in a cash flow structure or cash flow diagram are going to occur at discrete time points, separate time points, such as monthly payments or weekly payments. However, it is also possible to observe continuous payments as well. For example, $10,000 may flow into a savings account at a continuous speed throughout a month. These $10,000 is not going to be invested or deposited in the beginning or in the end. It is just going to continuously flow into the account, just like a water tap fills a glass of water. Okay, so the savings account is just going to be filled with cash at a continuous speed, continuous rate, and that is just going to be called continuous payments case. However, we are going to explain this in more detail when the topic comes to this point, and we are going to finalize with the interest rates varying over time. So what is continuous compounding? So we have said that the compounding of interest may occur more than once in a year. For example, under monthly compounding, we calculate a monthly effective interest rate, and we assume that the compounding of interest occurs 12 times a year. If we assume a daily compounding, in that case, the number of compounding occurring in a year will be 365. Now, you can indefinitely make this compounding period smaller. In that case, you are just going to get a continuous compounding. So instead of discrete time periods, you are going to have a continuous compounding occurring throughout a year. And we say that if equal time compounding periods, such as months or days, in a year is infinitely many, which means maybe every second compounding is occurring. Okay, so for the compounding periods are just seconds or even smaller than seconds. In that case, the compounding is just going to be occurring continuously. Okay, every moment the interest will compound. Now, continuous compounding is basically the limiting case of the discrete period compounding. Remember, in the discrete period compounding, the interest rate per year was calculated with this formula. Remember, R over M was the effective interest rate that corresponds to a compounding period, and the compound amount factor for a year will be calculated by taking this value to the power M. That is just going to be the compound amount factor for a year, and if you subtract 1 from that, you will get the annual effective interest rate. So this formulation was calculating the annual effective interest rate. Remember, R was the nominal interest rate. R over M was the effective interest rate that corresponds to a period. For example, when M was 12, R over 12 was calculating the effective interest rate per month. Now, in the number of months a year, which is 12, the compounding will occur 12 times, and that value will be giving you the annual compound amount factor, and we subtract 1 from that to get the annual effective interest rate. Now, what we are going to do is this. We are just going to take the number of interest periods per year to infinity. Instead of monthly, we are just going to assume maybe secondly, compounding. Every second, the compounding will occur. Now, the question here is this. How many seconds do we have in a year? Now, the number of seconds in a year is infinitely large. Therefore, in this formulation, we are just going to take m, the number of interest periods per year, to infinity, and we are just going to calculate the limit of this formula. And remember, this formula was giving us the annual effective interest rate. So what will happen to annual effective interest rate if we increase the number of compounding periods infinitely large? Now, it will become e to the power r minus 1, because as we know from the calculus course, the limit of 1 plus r over m to the power m is equal to e to the power r. The limit of 1 plus 1 over m to the power m was equal to the exponential value or the Euler value. So this number e is called the Euler's number, and this Euler number is taken to the power r because of the r value in the denominator here. So you see, if we have continuous compounding and the nominal interest rate r, then the annual effective interest rate will be e to the power r minus 1. So we can directly use the nominal interest rate to calculate the annual effective interest rate under continuous compounding. Now we need to understand this difference between the annual effective interest rate and the nominal interest rate under continuous compounding. By the way, continuous compounding is a very interesting case. So this chapter, what you are learning in this chapter, cannot be solved by any other formulation that you have learned so far. So you are just going to learn new formulations to solve questions under continuous compounding. Now, the question here is this. In a continuous compounding interest question, the payments may either be discrete or continuous. And first of all, we are just going to focus on the discrete payments case. So at this point, let's try to understand the difference between the nominal interest rate and the effective interest rate of continuous compounding. So a savings bank is selling long-term savings certificates that pay interest at a rate of 7.5% per year. So these savings certificates, if you keep them in your hand, they are just going to earn you interest at 7.5% per year. However, it says compounded continuously. So the 7.5% is the nominal interest rate, because compounding does not occur annually. If the question was to say compounding also occurs annually, then the nominal interest rate and the effective interest rate per year will be the same. However, here 7.5% is the nominal interest rate that is written on the contract, and we assume a continuous compounding, which is a new thing. Now, according to the claim of the bank says that the actual annual yield of these certificates is 7.79%, which means even though they are selling these certificates, which is supposed to pay a nominal interest rate of 7.5%, actually the people who purchase these certificates are going to earn 7.79% effective interest rate. What does this mean? The question asks. Actually, this is very easy. According to the formulation that we have learned in the previous page, we have said that in this question, the nominal interest rate is 0.075 as decimal, and under continuous compounding, the effective interest rate per year will be calculated as e to the power r minus 1, which is e to the power 0.075 minus 1, and that is equal to 0.07788 approximately. As percentage and the rounded value, it is approximately 7.79%, right? So you see, even though the nominal interest rate is 7.5%. The actual yield of this certificate as interest is 7.79 due to the continuous compounding. All right, so we have learned about the continuous compounding. So it is possible that the interest may compound every millisecond in a year. And in that case, the future value of a principal that is invested in a continuous compounding savings account can be calculated by using the compounding formulas, which are taken to the limit when the number of interest periods is infinitely large. So we are just going to do this. What we are going to do here in these pages, we are just going to consider every compound amount factor that we have learned so far. And we are just going to assume that the number of interest periods here are infinitely large. And we are going to take the number of interest periods to the limit, infinity. And we are going to see what happens to the compounding formulas or the compound amount factors that we have learned. And we are just going to replace our previously generated formulas with these new formulas if the question asks us, tells us that the compounding occurs continuously. Okay. Now, if the compounding occurs continuously, but the payments are made annually, still yearly. So in the end of every year, the payments are being made. In that case, how we are going to calculate the compound amount factors? So remember, F over P value, the future value of a principal, was evaluated as 1 plus I to the power n. Now you see, if the number of interest periods in a year is equal to m, then we calculate the effective interest rate for that period. And in the investment horizon, we calculate the total number of compounding periods as m times n. So this was the formula that we have learned in the previous chapter, chapter 5, which is replacing the classical single payment compound amount factor when the number of interest periods per year is equal to m. Now, what happens if we take the limit of this function as m goes infinity? It will become e to the power r times n, or simply e to the power rn, where r is the annual interest rate and n is the number of investment years. Now, of course, the single payment present worth factor will be the reciprocal of the single payment compound amount factor. Therefore, the ratio of P over F will be evaluated as e to the power minus Rn. Now you see there's a difference in the extended notation that we have used. Regularly, we were using the extended notation with ordinary brackets. But here, ordinary parentheses, here we are using square brackets. Okay, so square brackets. Why? Because if you want to solve a question that is under continuous compounding with extended notation, you should not confuse yourselves with the ordinary formulations. You see, under continuous compounding, the compound amount factors are evaluated differently, formulated differently. Therefore, in order to distinguish the problem with respect to its discreteness or continuousness, we are just going to define the extended notation of continuous compounding compound amount factors with square brackets. So this is a new thing. Instead of using ordinary brackets, just to distinguish that the question is related with continuous compounding, we will use square brackets. And the F over P value, or the single payment compound amount factor that is represented with a square bracket, will be formulated as e to the power Rn. Instead of the classical 1 plus I to the power n, we will have e to the power Rn. And the single payment present worth factor in a square bracket will represent the single payment present worth factor under continuous compounding, and it will be equal to e to the power minus Rn. Of course, these two were not the only compound amount factors that we have learned in chapter 2. We have also learned the uniform series compound amount factor F over A. So the classical formula for F over A was 1 plus I to the power n minus 1 divided by I. Now, instead of we are replacing the annual interest rate with the effective interest rate per period in a year, and the number of compounding periods in the investment horizon will be replaced with n times n. So this was the things that we have learned in the last weeks, actually. Now, if you take the limit of this function, the uniform series compound amount factor, when m goes to infinity, it will become e to the power rn minus 1 divided by e to the power r minus 1. Okay, so basically the I replaces with e to the power r minus 1, and here we have e to the power rn minus 1. So this formula is the uniform series compound amount factor, which is f over a ratio under continuous compounding, and here r is the nominal interest rate. So another difference in this extended notation is what? Instead of writing I here, I% here, we are writing R% because we are directly using the nominal interest rate in these formulations. Similarly, the uniform series sinking fund factor, A over F ratio under continuous compounding, or in extended notation in square brackets, will be the reciprocal of the above value, which is e to the power r minus 1 over e to the power rn minus 1. We have also learned the uniform series capital recovery factor, A over P, and A over P was ordinary in the regular way. It was formulated as I over 1 minus 1 plus I to the power minus n. However, since we are replacing the annual interest rate with the effective interest rate per compounding period R over M, and the number of compounding periods in the investment horizon is replaced with M times N, we have this formulation if these compounding periods are smaller than the years. Now, if you make these compounding periods infinitely small, and you have to take the limit of this function as m goes to infinity, and it will become e to the power r minus 1 divided by 1 minus e to the power minus rn. This is the uniform series capital recovery factor formulation for continuous compounding case, and the extended notation is again represented with a square bracket. And the uniform series present worth factor under continuous compounding will be formulated as 1 minus e to the power minus rn divided by e to the power r minus 1, which is the multiplicative inverse of the above function. Now, one final formula that we have learned in the third chapter, which is the gradient series factor. And the gradient series factor was ordinarily formulated as 1 over I minus n divided by 1 plus I to the power n minus 1. Okay, so this is our gradient series factor function. First, we are assuming that the number of compounding periods in a year is larger than 1. Okay, so basically the compounding periods are smaller than a year. In that case, we were replacing the interest rate with an effective interest rate of R over M, and we were replacing the number of compounding periods in the investment horizon with M times N. And now, if we take M to infinity, which means the number of compounding periods in a year is going infinitely large, which is basically continuous compounding. In that case, this formulation will become 1 over e to the power r minus 1 minus n divided by e to the power rn minus 1. Again, the extended notation for the gradient series factor under continuous compounding will be represented with square brackets and the nominal interest rate here. Okay. So, how are we going to identify these values? Actually, we have these formulations, but it is also possible that we may need these values in computation. So we will have a table for that as well. Now you see, so maybe it is best if I just share my whole screen with you in the first place to show these tables. All right, so you see in this folder, we have a second table, the compound interest factors, continuous compounding, discrete payments. So we are just going to assume the payments are going to be made again at discrete time points, for example, in the end of weeks or in the end of months or in the end of years. However, the compounding will occur continuously. In that case, the compound amount factors, which are formulated with these new formulas here, are going to be obtained also through this second table, which is named as compound interest factors under continuous compounding and discrete payments. And you see the single payment compound amount factor F over P, uniform series compound amount factor F over A, uniform series capital recovery factor A over P, and gradient series factor A over G can be found through these tables. These values are totally different than the values that you had in the previous table under discrete compounding. You see even the representation here in the headers are given as square brackets. Therefore, you should not confuse yourselves with this table and the previous table. If a question tells you that there is a continuous compounding and it is stating that the payments are made at discrete time points, such as monthly payments or weekly payments or yearly payments, in that case, you have to use this table again to identify values of compound amount factors. All right, so let's move on and solve a question related to this topic. It says a savings bank is selling long-term savings certificates that pay interest at a rate of 7.5% per year, but compounded continuously, and the continuous compounding is especially emphasized in bold, right? So you need to understand that we have to use square brackets in the extended notation if we are going to solve the question with extended notation, or you have to use the new formulas that we have learned in this chapter. So 7.5% is the nominal interest rate in this certificate. It says if a 10-year certificate costs $1,000, what will be its value at maturity? So this means if you purchase a 10-year certificate right now, you are going to purchase it from $1,000, and it will earn you interest at a nominal rate of 7.5% in each of these 10 years, but the interest will compound continuously. So what will happen to the value of the certificate in the end of the 10th year? Or in other words, if you just give this certificate back to the bank, how much money you are going to earn from that? Okay, so the present value of this certificate is $1,000. This is the amount right now you are paying, and we are interested in the future value in the end of the 10th year. The nominal interest rate is 0.075, and the future value can be directly calculated with the single payment compound amount factor. Okay, so we are just going to multiply the principal with the single payment compound amount factor, which is e to the power Rn, if you remember pages ago. So let me show that. F over P is equal to e to the power Rn. So we are just going to multiply principal with e to the power Rn, and 1,000 will be multiplied with e to the power the nominal interest rate as decimal, which is 0.075, and a 10 is also in the power, which is the number of investment years, and your money will become 2,170. So the future value of the certificate in the end of 10-year period, it will be 2,117. Now, of course, you can also solve this question by using the compound interest table we have just introduced right now, the second compound interest table. But for that, first you need to calculate the extended notation for F over P, the single payment compound amount factor, under 7.5% for 10 years. So if you are not interested in using the formula, you need to identify this value from the second table. But in the second table, again, we do not have any page that corresponds to 7.5% interest rate. Now, in fact, I can show it to you right now. So if we follow the pages again, we have 7% here and 8%, but we do not have 7.5%. So what we are going to do is this. We are just going to consider the single payment compound amount factor for 10 years under 7% interest rate, which is 2.0138. And we are going to consider the same compound amount factor for 8% interest rate, nominal interest rate, again for 10 years, which is 2.2255. Now we are going to take these two values and take the average of them, and that is going to become 2.1197 approximately. And when we multiply this value with 1000, again we are going to get a solution that is closely very close to the previous value that we have. So that's it basically. I mean, you can use the second table for continuous compounding. However, the payments should also be discrete again. Now let's solve another question to understand this practice better. It says a savings account earns interest at a rate of 6% per year compounded continuously. So in this question, the continuous compounding is not emphasized in bold, but I mean, you need to read between the lines, and you see we are in the continuous compounding domain right now. So we need to use the new table if we want to use the extended notation, or the new formulas if we directly going to use formulas. But the nominal interest rate per year is 6%. Remember, the nominal interest rate is always annual, the yearly interest rate. How much money must initially be placed in the account to provide for 20 end-of-year withdrawals? If the first withdrawal is $1,000 and each subsequent withdrawal increases by 200. All right. So in this question, we have a little different situation. So we need to draw the cash flow diagram for this question. Now you see our objective here is to withdraw $1,000 in the end of the first year, $1,200 in the end of the second year, $1,400 in the end of the third year, and we are just going to continue this process for about 20 years. Okay, so basically this is just going to continue for 20 years. So I have drawn a very, very long line here. Actually, the rest is not important at this point. The question ends here in the end of the 20th year. And what we know is this is just going to be 1,000. This is going to be 1,200, so and so forth. And this is going to be 1,400. And you see, we have a gradient series like this. And the question is asking us in the beginning, how much money should we deposit right now? How much money should we deposit right now so that we can withdraw these amounts in the end of 20 years, in the end of each year for 20 years. So the question is basically asking us this. Now, in this question, the only thing that is important is the continuous compounding. So we have a 6% nominal interest rate, but a continuous compounding. So if we are just going to develop the principal values formula on this gradient series, if we are going to convert this gradient series into the principal value, we need to use the extended notation under continuous compounding, or the formula that we have developed in today's class. So let's share our preview screen and check the solution. In this gradient series, the base amount in the end of the first year is $1,000 and the gradient amount is $200. Okay, in each year compared to the previous year, a $200 of increase will be observed, and these increase will continue linearly until the end of the 20th year. And the number of payments will continue for 20 years, number of withdrawals will continue for 20 years, and the nominal interest rate is 0.06. Now, what you need to do is, in order to calculate the principal value, you will decompose the gradient series into two parts, the base amount A0 and the gradient amount G. And the base amount will directly be multiplied with the uniform series principal present value, uniform series present worth factor, P over A under 6% nominal interest rate for 20 years. However, you are just going to use the continuous compounding extended notation with square brackets. And the second part of this decomposition is the gradient. How were we dealing with the gradient? We were converting the gradient into a uniform payment installments with A over G formulation, if you remember. So G will be multiplied with A over G under 6% interest rate for 20 years in square brackets. And then, since with this conversion it will become a uniform series, the uniform series can be converted into principal by using the uniform series present worth factor again. Now, actually, this is how we were solving such questions in the discrete compounding as well. However, the only thing that changes here is instead of ordinary brackets, we are using square brackets. So we need to understand that we need to use the continuous compounding formula. And according to the previous pages, the uniform series continuous compounding formula were developed as 1 minus e to the power minus Rn divided by e to the power R minus 1. And the under continuous compounding, the gradient series formula was formulated as 1 over e to the power R minus 1 minus n divided by e to the power Rn minus 1. So these two formula are evaluated as 7.30 approximately and 7.55. Now, plugging in these two compound factors into the formula that is defined above and plugging in A0 as 1000 and G as 200, you would get 28,368 approximately, which means right now you need to deposit this amount of money into the savings account so that for 20 years you can withdraw this gradient series of cash flows. Okay. However, remember the savings account is under continuous compounding with a nominal interest rate for 6% per year. Now, please at home try to solve the same question here, but this time just assume annual compounding, not continuous compounding, but annual compounding. Under the annual compounding, you will totally get a different value than this, because this time you are just going to use the values obtained from the first table. And if you use the regular compound amount factor formulations, again, you are going to get a different value than this. And in fact, in our future classes, we are just going to focus on that as well. So the next part where continuous compounding will be observed, but this time instead of the annual payments, we are just going to assume that these discrete payments are occurring in a different number of periods in a year, and we are going to study this topic in the next video.